The other day I was on a walk and I picked up this totally ordinary pine cone.
Oh, nice.
Yeah, and I was just staring at it, looking at how the scales perfectly open up to release the seeds. And suddenly that stack of research papers you sent over on composable mathematics and biomimicry just clicked.
Right. It's amazing when you actually look closely at those natural structures.
Exactly. Like I had decided, could we just copy paste this brilliant natural engineering straight into a 3D printer? So today's deep dive is for you. We're unpacking those sources to explore exactly that. Basically a breakthrough that allows us to compile matter end to end, taking biological observation directly into engineered manufacturing.
It is such a brilliant concept, honestly, because, well, it solves a fundamental problem with how we've always done biomimicry.
How so?
I mean, historically, when we're inspired by nature, the engineering is just completely ad hoc. We find a biological mechanism, try to mimic its shape or function, and then test it as an isolated case.
Right, so it's a one-off thing.
Exactly. The knowledge doesn't automatically compound for the next project.
So it's kind of like if you loosely trace a beautiful drawing by hand. You get a copy, sure, but you don't actually understand the underlying geometric rules.
Right.
If you try to resize it or tweak it, everything gets totally distorted.
Yeah, that's a perfect analogy. But the research you sent over introduces a totally different approach using category theory.
Okay, category theory, which sounds incredibly dense.
It can be, yeah. But to demystify it a bit, it's essentially the mathematics of translating between different structures. It gives us a way to say the exact way this pinecone bends is mathematically identical to how this plastic bends.
Oh, wow. So they mapped biological mechanisms across scales, right?
Yeah.
Like from a microscopic fiber all the way up to a macroscopic organ.
Yes, and they put them into strictly defined mathematical modules.
So instead of sculpting a single toy from a solid block of wood,
Yeah.
this mathematical framework gives us like a box of Lego bricks. We already know exactly how every piece will snap together. But wait, let me challenge this premise for a second. Because biological systems are incredibly messy.
Oh, absolutely.
So how can neat math equations possibly capture the sheer complexity of how a pine cone actually grows and adapts in the wild? Aren't we losing vital information in translation?
Well, we aren't trying to capture the entire living organism, just the precise dynamical mechanisms. So in this case, how the pine cone's physical hierarchy responds to humidity.
Oh, I see. Just isolating those specific parts.
Right, by isolating specific physical properties like heat expansion rates or moisture absorption, and writing them as explicit math equations, the software can calculate exactly how those properties interact. It guarantees they won't conflict.
Okay, so how does that abstract math actually become a physical object sitting on my desk?
So they translated that humidity-driven pinecone hierarchy into 4D printed active materials. They generated 4 different classes of actuators, which, are just materials that physically move.
Like strips that bend or twist.
Yep. Powered by either humidity or heat.
It's essentially automating the physical creation of active materials, which is wild. And, speaking of automation, since you're looking at integrating new tech into your own workflows this quarter, our sponsor Embersilk is incredibly relevant here.
Oh, definitely.
Yeah, if you need help with AI training, automation, or software development, they help uncover where intelligent agents can make the most impact for your business. You can check out embersilk.com for your AI needs. But getting back to the paper, the automation really is the crux of this research, isn't it?
It really is. The major breakthrough wasn't just copying the pinecone. It was using the framework to generate completely new designs.
Wait, so the software is essentially acting like a spell checker, but for physics?
That is a great way to put it, yeah.
So you're telling me they didn't design the thermal twisting actuator from scratch?
Precisely. Because the physical properties are written as equations, they just took a validated thermal module and combined it with a validated twisting module.
And it just knew they would work together.
Yeah. The software calculated that the physics wouldn't conflict before the printer even turned on. It generated valid G-code, which is the exact machine instructions for the 3D printer, and the prototype worked perfectly on the very first try.
Without any new derivation at all. That is incredible. So because physical systems are now formalized as composable math, we can just point artificial intelligence directly at these modules.
Yes, exactly. We already use AI to resolve long, open mathematical problems, right? Well, now we can point those same AI systems at matter itself.
So we can automatically discover and verify new physical designs in software before a single real-world prototype is ever even tested.
Exactly. When biology and mechanics become explicit, checkable, and executable, the speed of human innovation is going to absolutely skyrocket.
This is why this research is so highly relevant to the manufacturing challenges you've been dealing with. It represents such a beautifully optimistic future. I mean, scientific knowledge becomes executable infrastructure.
It gives us the tools to rapidly invent revolutionary materials and just, solve huge, complex challenges.
There is so much to look forward to. Thanks for letting us dive into these papers for you. And hey, if you enjoyed this podcast, please subscribe to the show.
Yeah, leave us a 5-star review if you can.
It really does help get the word out. Thanks for tuning in.
Thanks, everyone.
I'll leave you with this final thought to chew on. If we can mathematically compile a pinecone today, what complex, life-saving biological system will you compile tomorrow?